Hello, welcome everyone. My name is Dan Spurn. I'm the director of the Institute for Mathematics and its Applications, and it's located here on the campus of the University of Minnesota. For the past 20 years, the IMA has hosted public lectures by distinguished scientists whose work resonates with the general public. Past speakers have discussed topics ranging from the design of compact space telescopes using origami and the mathematics of the snow behind the movie Frozen, to cryptography and the need for mathematics for privacy on the internet. I'm especially pleased tonight that we can be back in person after several online public lectures. And after tonight's talk, we'll have time for your questions with the speaker. The IMA public lecture is made possible by the Arnold Family Fund, which has supported the public lecture series for over a decade. Thank you. I wish to express my thanks to Professors Calder and Arnold who are here tonight. And we appreciate their support. So on to our main event. Professor Manil Suri is Distinguished University Professor in Mathematics at the University of Maryland, Baltimore County, where his research is focused on finite element analysis. Though Dr. Suri has published widely in his field, he is also the author of 3 award-winning novels, including The Death of Vishnu, which has been cumulatively translated into 27 languages. He has co-authored the play, The Mathematics of Being Human, that has been performed at multiple venues, including the 2015 Joint Mathematics Meeting. He's a former contributing opinion columnist at the New York Times, for which he has written several essays on mathematics. His new book, The Big Bang of Numbers, How to Build a Universe Using Only Math, was written under a Sloan Foundation Fellowship and is the title of today's talk. Without further ado, please allow me to introduce Dr. Emmanuel Surya.
So I'm really pleased to be here, and thanks for that introduction, and thanks to the Arnold Foundation, or the funding for this lecture. It's great to see such a public forum for mathematics, and I was telling Doug Arnold that there are very few of these, so it's very precious to have this over here. So I'm going to be talking not about anything to do with my research, but something that I'm approaching more as a novelist. Like, how does a novelist look at mathematics? And what kind of narrative can you have? And that's kind of the loose idea behind this project, where mathematics, when you hear a narrative of mathematics, it's usually in terms of a historical chronology. And the thing with a historical one is things appeared and all sorts of results came in all sorts of ways, in all sorts of order. How do you actually arrange things so that one thing follows from another logically, and you go topic to topic? So that's the kind of challenge. But let me actually, since I like narrative so much, I think, well, I'll just use this. Since I like narrative so much, I'm going to actually give this as a story of what happened, and then we'll get to the main question of the talk: can you build the universe out of nothing? And it's really, well, we'll get to that. So the story begins in 1977 in Mumbai. I was a student. I was an undergraduate student, and that's the university tower there. And I was sitting in a math class by Professor Huzur Bazar. That was the name of the professor. He was our analysis and algebra teacher, and he gave us this famous quote by a chronicler who said that God gave us the integers and the rest all is the work of man, in the sense that, you start with the integers and then mathematicians build everything up. And then he said that, okay, actually, this quote is wrong because I can make the integers myself as well. I don't need God. So that was interesting, and he proceeded to show us how. And it's a construction that some of you, probably the mathematicians, have all seen. But this is, anytime you're talking about creation out of nothing, which is creatio ex nihilo, it comes up in religion, it comes up in physics, there's always some asterisk involved. There's always something that you're not quite starting with nothing. So let's see what he meant. And as I said, this is really a magic it's a magic trick. All of these are tricks of some sort. So the nothing that mathematicians start with is something called the empty set. Now, a set is just a collection of objects. You can talk about the set of people in this room, for instance. And for people who haven't seen set theory, you've probably seen Venn diagrams and so on, representational sets. So let's say that you have a set that doesn't have any objects. You essentially have something called the empty set, a set of numbers greater than, let's see, set of positive numbers that are less than -1, for example. Empty set of truthful politicians, empty set. So that's what you start with. So that's the little bit of something that you start with. You start with an empty set. And what mathematicians then do in this set theoretical argument is define that to be 0. This is what Professor Huzur-Bazar wrote on the blackboard. And once you have this, then notice what he does next. He takes a set that contains this empty set. So what that does is that now if you look at this bigger set, does it contain something or is it just empty? Well, actually, it does contain something. It contains that empty set that you just put in. So it's no longer empty. And so what you do is you've got something different from the 0 that you started with. So you equate that to be 1. You define it as the number 1. And what you do next is you can do the same thing. Take the two sets that you've actually just produced, 0 and 1, and enclose them, create a new set that contains both of them. Now you have a new set, and this set essentially contains 0 and 1. So it has two objects in it. We don't know the number 2, but we can kind of guess that we're going to actually define this to be the number 2. And if you think about this, you can keep going on. You can define 3 to be the set containing 0, 1, and 2. You can define 4 to be the next successor of that. And you can keep doing this. And of course, mathematicians, when they do this, have to have all sorts of axioms or assumptions to really set this right in rigorously in terms of logic. But as far as we are concerned, and as far as I was concerned when I was sitting in that room in Mumbai, it felt like Dr. Huzur-Bazar had actually lit some sort of fuse. And what happens then is that essentially what you get is you end up with all the numbers. You now have all these numbers, and that's what I call the Big Bang of numbers, as we shall see. But out of emptiness, you really created all these things. So that was actually a very amazing experience. It really, obviously the memory clouds and makes things up, but now I think of it as the closest I've ever been to a religious experience. Here were numbers that were just coming out of the blackboard and from what he had written. It was really, I hate to use this word, but it was really cosmic in some sense. You could think of creation in terms of mathematics, why not? And what happened between that time and, let's say, 2013, jumping, can't talk about all of this, but what happened after that was that I actually switched from being a physics major to a math major. Not just because of that one construction, but because of other things that he did in class. And what I did was I came to the US, I went to Carnegie Mellon, I did my PhD there, and after that I ended up in the University of Maryland in Baltimore County, and went up the tenure track ladder, did everything, got promoted, and then I started writing. It was a hobby. I figured that I didn't want to be just a mathematician. I wanted something else, so I started writing. And it was a wonderful secret life that I just would write maybe a story or two every year. And this blossomed over the years, and eventually I ended up writing a novel, and that novel came out in 2001, and it turned out to be very successful. It was translated into about 27 different languages, and suddenly my math was almost overshadowed by the writing. And just to cut this short a little, that led to another book several years later, and then a third book, and these books were collectively looking at Hindu mythology and looking at this whole cycle of creation and destruction in a metaphorical sense. Well, what happened due to all this writing was that the New York Times reached out to me and asked me if I wanted to write something about mathematics. And the article that I finally wrote was about getting to know and getting to like mathematics. And there were a couple of points that I tried to make in that. And the first point was that, when people think about mathematics, they think about arithmetic, they think about calculation. And they probably have fantasies that all of us who are mathematicians sit in our rooms and add long lists of numbers or something like that. So that's the kind of a thing that I wanted to swing people away from. Math is, of course, it's really about ideas, much more than calculation. And so that was a central topic in that story. And this came out, I think sometime in 2013. And it turned out to be a very widely read op-ed. And I woke up that morning and I tracked it. They used to have this most emailed list for the day, and it kept rising. It became #1 most emailed list. They had so many comments that they had to close down the comments section. Many of these comments were really like, I used to love mathematics. I used to be good at it in school, but then I got my job or I went into another field and I never really had a chance to do any mathematics. Some other comments were not so nice. They were like, okay, so you love mathematics. Here's a cookie, now shut up. So there were people who were also, on the other side. In any case, what happened was, by the end of the week, my article had actually risen in the most emailed list for the week. And it had risen to #4. And then I watched as it went to #3, and then #2. And then what happened was that the Pope started making all these statements about homosexuality and abortion and this and that. And he suddenly leapt up over me and landed in my #1 spot. And you might think that I have some sort of grudge against him. I don't, not much. I actually even sent him the book when it was finished. I'm not kidding. I got a thing back from him saying he's actually a character in the book. So I got something back from him, not from him, but from one of his employees, saying that the Pope had got my book, was blessing me and was blessing the book. So I guess there's not going to be a lawsuit. So that's good. But what I decided at that point was, my article had gone from the most emailed list. What I decided was I really needed to expand this into a whole book. And that's where this Big Bang of Numbers came out. And the idea behind this book was, can we start with that construction that Dr. Huzur Bazar showed me and go further? Like, okay, so you've created the integers. Well, what do you do next? And can you actually use that, keep going, so that you end up creating the universe? I said that, okay, religion talks about creatio ex nihilo, but it always has a supreme being. Physics talks something similar, but it has some sort of singularity or some sort of origin in that way. So there's always something going on that it's not really from nothing. So let's try to do this, and let's see, we might not succeed, but at least we'll know what extra ingredients we need. We are mathematicians. Anytime we are stuck, we add another axiom perhaps, or we change our assumptions. So can we do that step by step and actually see along the way where we run into problems and how to get around them? So that's the project. And incidentally, the book just came out in India, and I brought that up just because we're talking about Professor Huzur Bazar, who isn't here anymore, but I did dedicate it to him. So what I decided was, okay, to keep this religious theme, play with it a little, I would do it in the form of Genesis, where God creates the universe in 7 days, 6 days plus 1 day of rest. And I would do similar day 1, day 2, day 3, where we would construct different parts of mathematics. And they would actually lead to each other. That was the important thing. So day 1, we've already seen it's going to have numbers, and so it's really going to be about arithmetic. Now, I should just backtrack a little bit. I'd actually started writing something for the general public on mathematics way back in 2008, before my article came out. And it was going to be, a story. I actually had a name for it, the M word. You aren't supposed to mention it. And so that was kind of, I wrote about 200 pages, and I sent it to my editor, and she said, well, it was very charming. That's not a word you want to hear from your editor. Because what that means is, that's nice, but we aren't going to publish this. So when I started writing this book, I thought to myself, hey, I'm a novelist. I should write something that's fiction. Why don't I write a novel? Rather than do a nonfiction book, I'll write a novel based on this. And so that's what I did over the next several years. And submitted it to the editor. She said, we don't know how to sell this book. People who read books on math are going to want books that are nonfiction. People who read fiction are not going to want to read math. And that was it. So she could not actually, think of the right way to frame this book. So she suggested rewriting it as nonfiction. And so back to the drawing board, so that I rewrote it a third time, and this time I wrote it as nonfiction, but I managed to sneak by a few things which were carried over from the fiction. And so you have one thing that I thought of was to actually present the numbers as entities, as not humans, but as some sort of entities that are in some sense alive. And this idea actually came to me from a student who had synesthesia. And she told me in class one day that, all the numbers have colors, and when you write 4 in blue, it really makes me cringe, because 4, as everyone knows, has to be pink. And she had personalities for all these digits as well. So I kind of borrowed that idea, and the reason I use that in this book is because the numbers, once they're born, get to play games. And what games would they play? They would add, they would subtract, they would do things like multiply, divide, and things like that. And that's one of the things that I'm hoping through this technique, through this device, to show people, especially who are non-mathematicians, how much of a game mathematics is, which any mathematician would probably tell you. You enjoy mathematics because it's a game. You make up the rules, and then you see how far you can go. So that gives you a little bit of flavor of that. So what happens in terms of this progression, and I was talking to Doug Arnold just earlier today, and he was talking about a book on analysis that he teaches out of. And I said, wait a minute, that's the plot of my book. That's the plot of the book that I've written. Because what you do is you start with the whole numbers, 1, 2, 3, 4, and then you have addition and you have multiplication. And those, when you do that, you remain in that set of numbers. But then when you take the inverse of addition, when you want to undo addition, you start using subtraction. So these numbers play games, and 6 minus 2 is fine. Those two numbers can play the game and end up with 4. But 2 minus 6, and they don't have any place to go. They get stuck. And suddenly the whole universe has all these stuck subtractions. And so the way you progress is you start creating negative numbers. So that's how you get the integers. And the same kind of idea happens when you come to division, which undoes multiplication. Again, numbers like 6 divided by 2, you can do that. But 2 divided by 6, no, that doesn't work. So numbers get stuck again. And so that's how you end up with the fractions. You have to create new numbers to make up the fractions. And of course, that way you start getting, notice that they can be, expressed in terms of decimals. The numbers end up playing other games, like taking square roots. And that's when you find out that you need yet more numbers, and those are going to be the irrationals. They're going to be numbers which have decimal expansions that don't repeat, just like the fractions had decimal expansions that do repeat. And one of the interesting things that occurred here was, if you're building the universe, what use are these irrational numbers? Like, how do they actually help this universe that you're building? And when I ask mathematicians that question, the usual answer I get is that, hey, this makes things much more precise. If we want to measure something, we can measure it exactly. Well, except that, practically speaking, we don't really ever get the whole number. For example, pi, NASA uses pi to up to I think 13 or 16 digits, and that's enough for all their calculations. They don't need anything more. If you use pi up to 40 digits, you would be able to calculate everything in the universe up to the size of a hydrogen atom. So you really, it's overkill to start using pi up to 1,000,000 digits or anything. So back to the question, if it's not this extra precision, how does it help to have these numbers with expansions that don't end? And again, thinking about this universe that I was constructing, I realized that what the real benefit is that numbers like pi, they give you some sort of pseudo randomness, in the sense that if you start at some arbitrary position and look at the decimals that follow, you can sort of come up with some sort of random number generator. Of course, it's not really random, because if you know pi, you can list it. But for our purposes, it's going to be enough. For the purposes that we want later on, in terms of life emerging or things happening at random, that's probably fairly good. So that's one way of looking at why pi is important. And throughout this exercise, what I found was that if you're putting yourself in this mindset where you're actually constructing the universe, you sort of get a different outlook. You start getting these insights that are very different from the way things might have, the way we look at things. And one of them is that when you look at, and people who are mathematicians know that, there's a whole set of numbers which are imaginary, like the square root of -1. Well, when you look at complex numbers, the way I use them in this book is I use them in geometry. That's what inspires you to go from one dimension to two dimensions, and we'll come to that. So let us come to that. Day 2 is going to be geometry, and the reason for that is that these numbers are floating around, they're rambunctious, they need their own space, they need their own condo unit, and that's what you create the real line for. Creating a real line is interesting. I took as inspiration this quote by Kandinsky, who said that everything starts with a point. And it's a translation from Russian, so it's not clear whether he said point or dot, but he has an interesting kind of book on aesthetics, where what he does is he essentially looks at the blank canvas and he identifies a line as being made up of all these points. Now, of course, a point is very different from a dot. A point has no area. A dot actually has some area and gives you some pigment. His point was that when you're creating a painting, the first time you touch the canvas, your brush makes a dot. That's what he meant by everything starts with a dot. But when you look at this other book that he wrote, he was really talking about a line being made up of points. Euclid said something similar. He said that if you give me 2 points, I can draw a straight line between them. And not only that, his second axiom was that you can create this line segment between 2 points, and then you can keep extending it. And when you extend it, you get something that goes on forever, that is infinite. So what I'm doing in this book is twisting around Euclid's idea, where instead of Euclid was describing the plane, What I'm going to do is actually construct the plane. I'm going to assume what he assumed and say that, okay, give me 2 points. These are going to be extra ingredients. We don't have points from the numbers. We need to start with 1 point and 2 point. If you give me 2 points and you take Euclid's axiom to be true, you actually get all the points in between. And moreover, you can extend it into a line that goes on forever. So that's the mentality that we're going to use here. Once you create a line, again, back to Kandinsky, he said that the plane is just made up of lines. And you again need several axioms like the parallel postulate and so on, but you can start drawing these lines and make this ruled surface, which would be a plane. And you can go on. You can do this once you have a plane, you can stack these planes and a whole bunch of them, and what that would lead to is 3D space. And if you wanted, you could even stack up 3D space. If you could, we can't because we are stuck in 3 dimensions, but you could then actually create a 4th dimension just by stacking up all these 3D spaces, and this perpendicular direction is in a direction that we can't really see, so that's why we can't do it. And once you start talking about 3D, things get a little hard to understand. Like, we can't really talk about 4D. There's also this whole question of, remember, we are starting with this assumption that you start with 2 points and you magically get this line. Well, how do you know it'll be a straight line? There's nothing to compare it with. So you can't really be sure that this line, even if you assume there is a line between them, it could be perhaps the arc of a circle or something else. Interestingly enough, if you assume it's the arc of a circle, you can actually repeat the same construction, and what you will get is all these arcs of the circle, when they complete each other, they get a full circle. And taking a whole bunch of these circles in the same way as we did before will give you actually the surface of a sphere. So if you replace line by the arc of a circle in Euclid, what you end up with under some conditions is you get the surface of a sphere. If you replace it by something else, you might actually get a different surface. For example, something that has a different type of curvature, and this gets even harder to explain. So what I'm going to do is I'm going to show you using something that has nothing to do with math, and it's basically using crocheting. And this was an idea that Dana Taimina at Cornell University came up with. If you look at crochet, it's very similar to this idea of a line being made up of dots or points. Think about the line on the left. You're basically doing these knots, and you could keep going perhaps infinitely and create an infinite line if you had that capacity. You could also, if you look at the example on the right, you could try to create a 2D surface, but the example on the right wouldn't really work because the way crochet goes, it goes zigzag. So you wouldn't actually be able to, go very far. So what you would do instead is you would take a flat surface. You would make a flat surface by taking a circular pattern. And now, if you did this circular pattern and kept going, you would get something that is flat and planar. Well, if you look up crocheting books, you'll see that there are 2 errors that people often blog about in terms of how best to make a flat circle. One error that happens is what is called cupping. And this occurs when it turns out you're not putting in enough material. So you aren't putting in enough knots. So the surface, instead of staying flat, it tries to compensate and kind of cups in this way. And again, with the right conditions, there are formulas how this cupping can lead to a sphere. So this is one of those alternatives to the plane that I just talked about. And you can see it through crocheting. The other example that I didn't talk about, but I mentioned, there is this possibility. So that's the sphere. The other example is, and again, you can find this on crocheting websites, you'll find this thing called ruffling. This occurs when you're adding too much material instead of too little material. Now, when you add too much material, this material has to go somewhere, so it starts ruffling at the edges. And in fact, with the right conditions, you can end up with something quite spectacular. And this is what Dana Tamina did. She crocheted this, this object, which is really a hyperbolic plane. It's part of a hyperbolic plane. And so that's kind of the opposite of a sphere. Sphere has very little material. Hyperbolic plane has too much material. And so it goes out like this. Interestingly enough, the hyperbolic plane was something that was discovered when non-Euclidean geometry was discovered. And these ideas were basically very hard to translate. They were in the minds of mathematicians mostly, and she was the one who said, hey, you can actually crochet this and have something tactile with which you can interact. So it took humans, mathematicians, a long time to actually come up with something like this. But of course, these are used by corals and other life forms, and have been for, let's say, about half a billion years before mathematicians learned about it. That's kind of interesting that you have these other objects, other bioforms that knew about these things before we did. Kind of interesting. And what is the advantage of this? The advantage of something like this for a coral is that when you're looking at something that is filtering out all its food materials, it wants something with a very large surface area. So it wants a nice surface area to be able to do that. The spherical surface, on the other hand, you'll find that seeds are often spherical. And the reason for that is you want a very small surface area, because the surface is where most of the danger lies. You can prick the surface, and that's where something can go wrong to get at the nutrients inside. So you want to protect what's inside. So these are kind of opposites of each other. And the interesting thing is that when geometries were discovered, we did this in 2 dimensions, but you can also have 3-dimensional stuff like that. And in fact, that's one of the things that Einstein used in terms of the space-time being curved. You often hear that. So this gives us a way of actually trying to put our minds around what happens in a 3-dimensional analog of this. In other words, what does it mean for a 3D space to somehow become curved? What would that mean? And the way I think about it is, once again, think of some sort of crochet, or maybe you're adding material, dot by dot, knot by knot, making this whole 3D stuff. Maybe you think of it as a pastry bag where you're adding material, and that's what's creating our 3D space. Now, if you don't put enough material, then what's going to happen is there's not going to be enough, and things are going to curl in on themselves, much like the sphere does, much like that cupping happens. If you put too much pastry cream in, then it has to come out somewhere. It has to ruffle. Well, it won't come out in a way that you can see it. It'll actually ruffle in this 4th dimension. It'll be squeezed into the 4th dimension that you can't see. And so that's what the analog works, how the analog works when you look at a higher dimensional version of this. Okay, so we've got these two. Let's see, what would day 3 be? And I've told you how long it took me to finish this project. And while I was doing it, I made all sorts of little videos to keep me going in PowerPoint. And they're very silly, but they're kind of fun. So for day 3, I'm just going to present you this video. Watch the way that the numbers appear. They actually appear in the same order that we talked about in day 1. So let's see what this video is. And that'll tell you what day 3 is about. Okay. Somehow the sound isn't coming. I don't know why. Okay, now it's there. So the title is actually pretty nice because algebra is the way that you actually get a way to speak about mathematics, to translate it, to transfer it to somebody else. And this is going to be important in terms of our creation, simply because at this point you're really, or I'm really, stuck with a real problem, and which is that how do you actually use mathematics to create anything physical? I mean, that's a real issue. Like, okay, it can create theoretical stuff, but something physical, well, that's hard to do. So what I did at this point is, again, looking at what else I would need, I would need some sort of external agency to actually do the construction. And this might sound like really cheating, and maybe it is, but on the other hand, think of all the great builders that you've had over history. Shah Jahan, he didn't actually use hammer and chisel or mortar to set the Taj Mahal in place. So building, I'm going to take in that sense that you're building a house, but you contract it out to an outside contractor. And this outside contractor is going to be nature. And nature can be something that you define. If you want to think of nature as God, fine. If you want to think of it as something like physics, fine. But you're going to need a language to actually give your instructions to nature. And this brings us to the next, and so algebra is the way that you actually manage to do this. This brings us to day 4, and I'm just going to give you a few glimpses of all these days. So day 4 is going to be patterns. And you can talk about easily with mathematics, making patterns like fractals and making patterns that involve different geometries and so on. I'm going to talk about something, again, picked out from this day that's very interesting, and that is, if you're talking about the whole universe being created, does math actually speak to things like beauty or aesthetics? And when you start thinking about that, the kinds of thoughts that often come to your mind are things like the golden ratio, for example, where that's supposed to be something 1.618 discovered all the way back in the time of the ancient Greeks, but made popular in around the 1500s by a mathematician by the name of Luca Pacioli, who wrote a book called The Divine Proportion, and said that this is a ratio that gives us harmony, that feels perfect. And his pal, Leonardo da Vinci, actually constructed about 60 drawings for a book that Pacioli wrote. And so people always wonder whether Leonardo actually had something to do in terms of the golden ratio, whether he used it in some of his compositions. And so this golden ratio is, as I said, 1 is to 1.618. And if you look in the literature, you'll actually see a whole bunch of papers in plastic surgery where they have looked at this ratio and tried to determine whether, when they're using their scalpel and so on, whether they should somehow incorporate the ratio in terms of the distance between your chin and your nose as opposed to your nose and the center of your forehead. So they've tried to optimize that, and you will also see some ads talking about that. Not that I was looking at ads for plastic surgery, but you can find those on the web. As I said, this is supposed to be a proportion that is supposed to be very pleasing to the eye. And the theory is, by some people at least, that this is why the Mona Lisa is so beautiful, because her features fit right into the golden ratio. So that's one kind of aesthetic that mathematics provides us. The other kind is in terms of symmetry. And we know there's a whole theory called group theory that talks about the symmetries of an object, but this theory says that aesthetic value comes from symmetry. And you can compare different figures and figure out how symmetric they are. For example, you can count how many axes a certain figure is symmetrical about. If you look at the rectangle, then you find that you can only flip it either this way or this way. If you look at a triangle, then it has 3 axes and it remains the same no matter how you flip it. And if you look at the square, it actually has even more. So in that sense, the square is more symmetric. By this token, the hexagon would be even more symmetric than the square. And if you look at the circle, that's going to be the most symmetric because it's symmetric across any axis. Now, there's a theory by famous mathematician George Birkhoff in 1936 where he actually tied aesthetics to symmetry and claimed that this is what makes something beautiful, the number of symmetries that you have. And so let's test this. Let's see if it works for the Mona Lisa, because the problem with her is that she doesn't have any axes of symmetry. Like even bilateral symmetry, she's not bilaterally symmetrical. So what we're going to do is we're going to try and give her a mathematical makeover. Try to make her more beautiful. I mean, Leonardo tried, but we can do better. We are mathematicians. So what I'm going to do is I'm going to, first of all, just take half her head off, and then duplicate what she has on the other side. Well, that doesn't look very nice at all, right? So what we have to do is stretch her out again, just to get the right aspect ratio. Still not very good. So let's see, what else can we do? Well, let's give her more symmetry. So let's do this. Okay, now she's too long, so let's squash her a little bit. Okay, not so good. So maybe more symmetry. We talked about those 4 lines of symmetry. So what if we actually made her symmetric across the diagonals as well? That's what we saw with the square. So let's do that. So let's take one piece of her and then duplicate that. Well, that really doesn't look good. She's actually lost all her facial features, but there's a better way to do that. And the thing that we did wrong was we didn't take the right piece. So let's take that. And does that look better? Little better? No, I guess more like a bloated something, like a soccer ball or something. Well, there's one way to fix this. And we just need to plug on. We shouldn't give up hope. Birkhoff was probably right, so we need to trust him. So let's see what happens if we scrunch her up a bit and then, make her into a hexagon. Okay, well, that's a little better. You can twirl her around now, so that's nice. But let's say that we want to go further. So that's actually not so bad. Well, if we can do that, why not make her, tiny slivers of Mona Lisa and put all these together. And notice what we get. In this limit, we'll actually get a circle, and she's now blended together, and that's actually quite aesthetically pleasing. So that's the limit that Birkhoff was talking about. That if you really go in this direction, you essentially get 2 different aesthetics. One is the Mona Lisa type, and the other is this other aesthetic, which is a more blended kind of symmetry, beauty, whatever you want to call it. Now I can see that people are very skeptical about this, so I'm going to give you another example. And people say, hey, math, this kind of math has no applications, so I'm going to actually apply it for you. And since election night is coming up next week, let's take 2 people, and chances are that everyone in this room probably finds at least one of them very scary. On the East Coast, I just give Trump, but I didn't know how the politics work out in this state, so I decided to be safe and put both of them there. Let's try to do the same thing with them. And I'll just give you some of these. So if you actually give them the same symmetry as a square, this is what they look like. And that's very scary, I agree. Yeah. If you start going along with more pieces, then they become a little less scary. And if you go to the limit, which I did, they're pretty harmless. You can actually hang them up on your wall. In fact, maybe some of those are like that. I don't know. So again, there is something to be said about this idea of math and beauty, symmetry and beauty. At least for them, I think it made them more beautiful. Okay, so let's now go on, and just a few slides left because we're running low on time. The next step after all this was physics. And here, I was kind of like, okay, how am I going to pull this off? I mean, physics is enormous. To talk, to even scratch the surface would take hundreds of pages to actually explain. Well, in 1900, the famous mathematician Hilbert came up with 23 problems that he said were the greatest unsolved problems in math. And number 6 was the axiomatization of physics. So he wanted to take the more computational parts of physics and show how they all derive from a list of axioms. And that is sort of what we've been doing right from the beginning, right from what Dr. Huzur Bazar did. And so I said, okay, maybe I can just kind of finesse it and say, okay, those people have been working on this, and we'll just imagine that they'll do what's needed. And what I contented myself with in terms of this book was just give a couple of examples where physics really derives from mathematics. The primary example is Newton's law of gravitation, the inverse square law, where gravitation is supposed to depend on 1 over r squared, where r is the distance between two bodies. And that really follows just by looking at the surface area of a sphere. And you can find that in many textbooks. And then, of course, we already talked about this other idea of how the geometries that were discovered way back in the 1900s or 1800s were then used to figure out space-time. Now, this is a point where a very interesting question arises, and that is, how did this happen? Like, examples like this happen all the time in mathematics, that people discover things, they do pure mathematics, they're just looking at abstract ideas, and then they do their stuff, and then many decades later, or even centuries later, somehow these ideas turn out to be the perfect things to actually explain our universe. For example, all the way from conic sections like ellipses and circles that were discovered way back in prehistoric times, and then were used by Kepler to describe planetary motion. How did that happen? Why did that happen? And of course, one way of looking at it is that mathematics is about the study of patterns, and so we actually look at things, extract the patterns, and that's what gives us mathematics. But the way that we're looking at in this lecture is the way that Plato would have thought about it, and he thought that everything in mathematics existed in its own ideal universe, and that we often sometimes get glimpses of that and somehow can use mathematics. So that idea is that mathematics is actually inherent in the universe. It's ingrained in the universe. And so the kind of exercise that we're doing in this book is perfectly logical and should make sense just because we're actually just uncovering the kinds of mathematics that have already given birth to our universe. Maybe I don't have the details right, maybe I'm using some extra ingredients, but in terms of the philosophy behind it, it's plausible. So that's a good point to think about these things. Day 6 was infinity, and this picture actually comes from the title of that novel that I wrote that was nixed by my editor. It was called The Godfather of Numbers. And the idea was that infinity is always behind a lot of math, even though we never actually attain it, never achieve it. It really plays a role in a lot of things that we do, theoretically and in some sense practically as well. And I should just point out that another thing that I managed to get past my editor was a whole story, a short story about different types of infinity. So that's somewhere in the book. Okay, and that brings us to the last day. And day 7 is supposed to be a day of rest, if you remember in Genesis. And in the same way, something's going to happen with our universe as well. Because one of the things that happens along the way is that we set into motion a whole bunch of input-output type algorithms. What do I mean by that? The technical word would be something like a dynamical system. But what I mean is something like the forces of erosion that work slowly to shape coastlines, or I'll give you this one example: things that are started up and have some pretty interesting results when they're repeated again and again. The coastline, for example, it's little bits of erosion, little bits of waves that go on through centuries. You can think of the coastline as a series of pictures. Taking one picture as the input gives you the next picture as the output. Taking that as your new input gives you the next picture as the output. And you keep doing that. And through these little bits of erosion, very simple effects, you eventually end up with a coastline that looks very amazing, very complex. The same thing can be done with fractals. If you have looked at how fractals occur, very simple rules give rise to very complex behavior. I'll give you my favorite example of this, and this is if you look at ants, you'll find that when they're looking for food sources, they'll cover many different paths. And what happens eventually is that they manage to optimize, they manage to find the shortest path. And how do they do that? Again, by a very simple rule. What they do is they drop pheromones which other ants can sense. So as the ants start, if you look at the lower path, it's shorter. So let's say initially the same number of ants are going in the two paths. The lower path is shorter, so there's going to be more ants that quickly finish that route or finish it quicker than the ones on top. So there'll be more scent deposited. And as the number of ants, it becomes a cycle. As the number of ants increases in the lower portion, there's more and more scent over there, whereas there's much less up there. And so eventually you find that you just have the lower portion left. And so they have optimized things, this kind of swarm intelligence, which emerges without with a very simple rule. So the last slide in my talk brings us back to a very basic question that I just alluded to, and that is, what is the nature of mathematics? And how does it tie in with creation? What does it tell us about ourselves? One of the things that I think is probably true is that in terms of ourselves, we can't really tell whether are we here just because of chance, some random chance? If you're more on the agnostic, atheistic side, that's what you probably believe. If you're more religious, you feel that, hey, maybe you've been put here on purpose. It's someone's doing, someone's cognition that has led to you. If you look at mathematics, that's the same kind of dynamic in math. One possibility is that we actually create math, that it's something that arises in our mind. We do it for a purpose to actually explain the universe. And it's very much something that's cognitively defensible. The other possibility is that math is something that is out there, like Plato said. It just arises by itself. These numbers that we started with, whether we were here or not to appreciate them, they would just occur. You could always have emptiness, and that could always be thought of as creating numbers. So do you need humans? Is it something that occurs naturally due to randomness, due to chance? In some sense, that's the same metaphor that we struggle with, or we might not struggle with. We might just set it aside, but it's the same kind of duality that we find in our own lives. So I'll end there with this final metaphor. and thank you for listening.
Dr. Suri is taking questions, but I think we should bring the microphone down. Professor Suri, how would you relate this notion of creation to religious creation myths or physics creation myths? I know you touched upon that a little bit, but maybe you could expound a little bit more.
So I guess I kind of leave it to people to decide where they live on that spectrum. First of all, I looked very carefully to see whether there were creation myths about math being created. And there's one or two things about numbers, but very minor. So there's not really any myth that has occurred in that sense. If you look at something like geometry, notice that when you look at Genesis or you look at Hindu mythology, Brahma breathes out the universe in a single breath. God creates all these things in Genesis, but the thing that is never talked about is you need some sort of empty space beforehand to put in all these creations, to actually hold them. And it's up to us mathematicians to fill that gap. We can't, people ignore that, it's never talked about, but how did you get empty space? It's not the same as nothingness. And so I think things like that were part of the more interesting things to work with. Now, physics, of course, does talk about empty space, how that was created. Many theories in terms of expanding universes basically posit that space is created. The Big Bang is an explosion of space, not in space. So the space is actually being created as the universe is expanding. So they actually do talk about that. But it's interesting to divorce that from the mathematics, just because we can get another insight, rather just looking at space itself. Because physicists will say, well, you can't talk about space without time, and that's true, but you can certainly arrange things in your mind better if you talk about them separately. Yes.
There's this idea that the universe could be periodic. Let's say in 100 trillion years, it could be all back to this room and
Right.
So if you have a universe like that, then let's get rid of the problem of saying, well, what happened?
Well, so what your question is about universes being periodic, and that gets rid of the, what happened before. And I just barely touch on that, but here's what I would say in response. Physics is very different from mathematics. That's what I ended up realizing, just the discipline, in the sense that in mathematics, we have to make certain assumptions, and then we build up from there. And so mathematicians generally agree on a lot of things. Physicists, on the other hand, they come up with theories that'll fit the data, so it's an experimental science. And when you get to things about creation, and as you get closer to origin theories, there's a lot of things you can come up with. And essentially, there are different competing theories, and it's a big marketplace, and the theories that coincide with any data that comes out later, they're the ones that win. So you talked about this theory about things coming back full cycle. Well, as I was researching this book, there were many other things that were, there's one paper that talks about like the universe being one-dimensional at one point and then growing a second dimension, then a third, and now apparently it's trying to grow a fourth dimension. There's another theory that says that the universe is actually a facet on a higher dimensional reality. So it's like the surface on a cube. And there are many other theories too. And I found it very difficult to actually keep all these theories and try to make a sensible narrative that still managed to, at least mention some of these theories. Yeah.
If there was a big bang out of which mathematics was created, could we look forward to a big crunch in which it all falls in itself?
Well, that is the question. I guess certainly if we think about mathematics as being created in our minds, then the big crunch would be our extinction, which certainly could happen.
Just one more. You've talked about beauty, symmetry, emergence, things that go with the evolution of the universe. I wonder what you think the role of mistakes is.
So interestingly, I in the book somewhere, I do talk a little bit about that in the following sense. If you look at this idea that the universe is all following the pattern, nature is somehow following a mathematical pattern and coming up with mathematical forms, first question that arises is, why does she do such a horrible job of it? I mean, if you think about triangles, there's no real triangle in the universe. It's always a little off. If you think about fractals or patterns, it never goes to infinity as it should, just as a few layers and then, it's okay, that's good enough. So everything is kind of approximate. And in some sense, I don't know if that's errors or if it is just, the way I interpret it is that nature is trying to put her own mark on this. It's sort of like, one of those Persian carpets where they weave in mistakes in purpose, just so that it's not jinxed in some way. So that's the take that I give in this book.
Hello.
Hi.
Well, I really wanted to ask something else, but I think at the moment I'm here to defend myself as a theoretical physicist.
Okay.
Well, I think mathematics and physics are something that are quite similar to each other, despite the odds and differences. And I think I realized it when I more figured out about how physics is more or less a model of the way we describe things. And since I'm a theoretical physicist, I seem to understand that since we go on abstract ideas like numbers, real numbers, imaginary numbers, complex numbers, and then we have transcendental numbers, in physics, the ideas are not yet concrete. The ideas are still abstract. Energy, momentum, all these ideas are still numbers. They are not something that is physical. I used to believe that they are physical, but they're not, because when I study more physics, I figured out that, oh, wait, energy can become imaginary sometimes, or momentum can become imaginary sometimes. If things cannot remain in the same plane in physics, we can be very sure that these things are as abstract as numbers are. So if you're saying that even without us, math can still exist, is it a possibility that there is a physical way we can define these quantities, and even without us, those quantities would still physically exist?
Well, again, I'm not a physicist. So what I have read about some of the questions that you're asking, I'm trying to recall this person's name, but this was a book about 2 years ago or so. But one of the things that, and you can find other references, is whether physicists, theoretical physicists, whether what they're doing is mathematics or is it physics. And by physics, I think the writer of this book and other people are really defining physics in a much more restricted way, in the sense that it has to actually be somehow supported by empirical evidence, by experimental evidence, which, of course, when you go back to origins, you can't do. So I agree with you. It is certainly a spectrum. I mean, it's whether you call it physics or mathematics, it's very mixed. But again, there are people in the physics world who, I have a colleague, for example, who said the multiverse is basically a fraud, hoax and so on. He had lots of, and he's a physicist. So I don't know. It's the nice thing is that physicists can decide amongst themselves, and we mathematicians, will accept the answer you give us.
Thank you for the privilege.
Yes. So
Here's a mic.
Every once in a while, you hear theories that the universe is a simulation.
right.
It might be a program running on God's laptop or something like that. And there have been real discussions about how, if that were true, we could distinguish or recognize that fact. And it might be exactly the kind of lack of infinitude or that finiteness that you've mentioned. Do you address that concept in your book at all? Or do you have any thoughts on it?
So your question is whether I address the concept of figuring out whether we are in a simulation, in a computer simulation or not. I think the closest I come to is, you talked about infinity in some sense, whether things are finite or infinite. And the day on infinity, one of the things that one has to think about is whether we ever actually experience infinity. One possible way that we could experience it, and it depends on how you interpret things, is that if you look at any instant of time between now and, let's say, 2 seconds from now, I can divide it into a whole bunch of tiny pieces. I can divide it into a bunch of instants, let's say, and to live from this point to 2 seconds from now, one could argue that I have gone through an infinite number of instants of time. Now that's fine, but again, when you come to physics, then, and again, I shouldn't be speaking this because I'm not a physicist, but from what I understand, if you look at more quantized quantum theories, then you have a limit where beyond that, you can't really talk about continuous time. So in other words, there's a minimum time period, and you can think of us as existing from one quantum to another of time. So it's like when you see bulbs on a marquee, they're flashing on one after the other, and we are kind of hopping from one existence to another. So in that sense, the fact that we don't have infinity wouldn't necessarily show that we are not in a computer simulation, because computer simulation would be somehow finite, but there are theories that sort of depend on a finite, finitely dense universe, finitely dense time.
So I was just curious, like, where would you place in your religious analog or maybe philosophical analog something along the lines of like Russell's paradox or the incompleteness theorem?
Yeah, so the incompleteness, Russell's paradox, I mean, both of these, I mentioned these in the book. Russell's paradox basically showed that, I kind of very casually said a set is a collection of objects, and it turns out you can't do that. So anything you do in mathematics, there's usually a problem, and you have to go deep and fix everything. So Russell was the first person who proved that. You can't just say a set is a collection of objects. The reason is that then you talk about the set of sets, and you come up with logical contradictions. So he actually was the first who started, figuring out what the axioms, what the assumptions should be. That's one point. The other point about incompleteness is something that Gödel came up with. And what he showed was that essentially, if you have any system of logic where you have gone, where it's complex enough to talk about arithmetic, if there's some system of logic where you can talk about arithmetic, some mathematical system where you can talk about arithmetic, then you can always make statements in that system which cannot be proved either correct or incorrect. You can't prove. They might be correct or incorrect, but you can't prove them if you stay in that system. And the example, the loose example that's given is, that this statement is false. Look at this statement is false. Well, if it's false, then it's true. But if it's true, it's false. So, you can't really prove that. Anyway, his thing is much harder. But again, it's a question of, is that a metaphor for something? And what I feel is that, okay, so math is sort of the highest endeavor in terms of human thought, I feel. If you think about it as being constructed in our minds, which we have done in some way or the other, it's really the highest way that we can describe or interpret the universe. And if even that has incompleteness in it, if even with that we can't really answer certain questions, then maybe other forms of endeavor are going to be equally lacking. And so maybe we shouldn't be so hard on religion, perhaps, I don't know, that it doesn't give all the answers, and it can't, maybe, I don't know. The Pope, however, would be happy to know that Gödel's theorem doesn't really show that there is no God. You can't use it for that because God would be outside the system. So it wouldn't really work on that.
I was wondering what similarities you found between writing novels and doing mathematics, since these seem very different activities.
They're both very difficult, I think. That's for one. And they both take a long time, and you have to do a lot of rewriting in both of them. And this was kind of funny because it went back and forth between one and the other. I did find that in terms of writing this as a novel and writing this as nonfiction, the novel, the problem was that if you're writing for a general audience, you can't expect them to pick up different references. Novel writing is all about allusion. You don't say something, you don't hit people over the head with a hammer. You have to just allude to things. Well, I found that trying to explain something in the format of a novel just made it very voluminous. And even though some people liked it, it just was so difficult and just, was too weighty. And so actually writing it as nonfiction was the correct choice. And I have to thank my editor, even though she made me struggle for all those years. It did turn out to be the best choice for that.
I think we have time for one more question.
Hi.
Hi.
Thank you for the very interesting and fun talk. I was just curious how you landed on Genesis as sort of the structure of the novel, if that was a holdover kind of along the same lines from the fiction version, or how that came to be.
No, thanks for that question. So I think I always had this idea of, how geometry arises from the numbers and how algebra comes from geometry and then patterns from algebra and so on. So I was going to do that. But once I put the Pope in, and the Pope appears throughout the book, and he basically gives the religious point of view. He's musing about whether you can have a perfect triangle in the world or not. And incidentally, the Pope, as some of you probably know, when he was in school, he studied science, he studied chemistry, and he worked for a while in a chemistry lab. So he does have this possible strain of science that he also incorporates. So I use that a lot. So there were several examples of religion and mathematics, and one of them is Cantor, of course, who developed the whole ideas of infinity, where he was very scared that he might be the next Galileo. And so he was always showing because he's talking about infinity, and that's such a, possibly blasphemous topic. So he was careful to send his results to various bishops, and one of them actually endorsed his result. And then he actually sent his results to the Pope as well, much like I sent my book to the Pope, I guess, though I'm certainly not comparing myself to that. But your question about Genesis, it came towards the end, right at the end, where I said, hey, you know, I have 7 chapters and there are 7 days of Genesis. Why don't I just, you know, basically list them in that way?
Before we end tonight, I just want to let you know that Professor Suri will be signing books afterwards. And before we leave, let's thank our speaker tonight. Thank you so much.
Okay, thank you. Thanks. Oh, yeah, thank you.